Good day. My name is Lakwa Selamugo, and today I'm going to be presenting my artificial intelligence assignment. And the title for my assignment is an integrated machine learning pipeline for diabetes risk assessment and patient stratification using BRFSS data. In my first cell, of which I'd call my first session, it indicates the necessary libraries that I'm going to be importing, and in this cell we load our dataset, which is the CSV file for diabetes binary health indicator. And in this comment we can actually just like emphasize on the functionality of what it can do to the rows. For example, I can actually just put 10 and then run it, and then it should actually just give me 10 rows. As we move forward, I'm going to just go through the next cell, which is to remove duplicates. In this session, we're going to remove duplicates. As we see here in our comment, we're going to create a visualization with a bar and a chart to demonstrate all this and to show from which section that actually has all the things that actually has to be on this thing. We also have the pie chart for duplicate distribution, of which is going to show, as well as the bar chart here. And now we can also just actually have to go through the fact that our original data set, before we actually had any duplicates, it's just in this initial part here, and after that it went to this part. So that means that here is our duplicates that we have actually just even showed through the data and through the bar chart, and as well as the pie chart. As we move forward, we go to the diabetes disease distribution. In this, we are going to actually have to just visualize the distribution of diabetic versus non-diabetic patients, of which is going to show that the count, we're going to count how many patients have diabetes versus those who are healthy, and we're going to print actual numbers for non-diabetic and diabetic patients. And as you can see, that the green bar demonstrate those without diabetes. No, yes, without diabetes, and the red actually just indicates those themselves that actually have diabetes, and hence our output, diabetes prevalence in patient population, non-diabetic. This is the number for the non-diabetic people according to the total, and these are the diabetic patients, and the prevalence rate is 15.3%. And we move on. You go through the clinical correlation matrix. We're going to select numerical features for correlation analysis, and in this we're going to actually have to just visualize correlations to identify relationships between clinical indicators and diabetes. And this is going to be the session that is going to actually have to just determine of which has the highest, strongest correlation with diabetes. Normally we indicate it by like the color, whether it's just too brownish and too reddish. Hence we see in our output here that the strongest diabetes correlation, it's high blood pressure. We have high blood pressure. We have high blood pressure is one of the leading ones, as well as the high cholesterol. We have body mass index as among those that are leading with all that. So basically, we can actually summarize this session by saying that we're going to compute correlations among numeral features, plot heat map to visualize features, and strongest correlation highlight predictive factors like age, BMI, and high BP, as we have indicated in our markup comments. In the next cell, we are going to create a simple health risk score, of which is the sum of the high blood pressure and high cholesterol flags. Create a BMI category. 1 is equals to obese, and then there is non-obese. We're going to prepare features X and target for diabetes prediction, split data into training and sets to evaluate model performance. We also have like the logistic regression baseline predictive model. The random captures nonlinear, and in this session we are going to create health risk score, of which it includes BP plus cholesterol and body mass index category, which includes obesity flag to capture key diabetes risk factors. We prepared features and target, then split and scale data for modeling. Quick model check logistic versus random. So this is the comparison, and we have actually just used a 3D plot to just actually plot the body mass, and the age, as well as the health risk score. As we can see here, the body mass, the age, and the health risk score, which among all these scatters themselves represent that the red are those that with diabetes and the blue the non-diabetic. As we move on, we have the pie chart, of which is just demonstrated here, and in this session we group patients into natural risk categories using age, body mass index, and health risk score. We have K-means clustering, of which is 3 clusters, as we can actually see them here. In the high risk obese, the hypertensive moderate risk, and the healthy low risk. As we move on, here is our output that actually shows that the hypertensive risk, it actually is more, and this one, the healthy low risk, is the one that actually is the green part. The high risk indicate by the color red, and the moderate we indicate by the color yellow. We move on again to the next session, of which is session 7, and in this session we're going to actually have to just talk about patient health profiling, of which we visualize patient risk using body mass index, age, and health risk score against diabetes status. Scatter plots highlight high risk patients and high body mass index plus high risk score, and we also help identify clusters of patients with elevated diabetes risk, support clinical insight among the young and healthy, low risk, older, high body mass, and high risk, as we have actually just showed here, according to the age and the health risk and body mass index, indicating that those that are young are less likely to be diabetic, and those that are actually older are more likely to be diabetic or actually just affected by diabetes. As we move on to the next. In this session, we're going to talk about the diabetes neural network comparison with training progress, of which we're going to actually have to just compare 3N configuration to see which best models diabetes risk patterns. We have the small neural net, medium neural net, deep neural net, and in all this we're going to actually build N for diabetes risk. We're going to train the model, the N lens nonlinear and all risk patterns. We're going to evaluate prediction on unseen diabetic and non-diabetic patients. We will run this cell again to just see the training while in progress, to just show what it does, of which the training small neuron has to go first, and is training the first neurons. And it's done, leading to more training of the medium neural network. By the way, this is the N. The diabetes neural network comparison with training progress. It's training the medium, and the medium is done, and now we are about to train the deep neural network. Perfect. Now we have all trained our three sets that we actually had, which is the small neural and the medium neural network and the deep neural network, and it has actually just shown the diabetes prediction accuracy and the training time. Hence, if we may summarize it, we may actually just say small net learns basic diabetes signals, example body mass plus age effects. Medium neural models more complex metabolic interactions. The deep neural captures deeper nonlinear risk relationships across multiple features. Each model was trained on 80% of the dataset and tested on 20% unseen patients, ensuring fair evaluation and preventing overfitting. A visual comparison was then generated to display. So here we have our prediction accuracy, which is actually how well each N identifies diabetic versus non-diabetic patients. The training time, of which computational efficiency of each network. As we move on to the diabetes model comparison, we're going to do and actually show the diabetes model comparison, of which we have logistic regression, random forest, linear SVM. And in this session, we are going to compare multiple machine learning models for predicting diabetes using clinical features, body mass index, age, high blood pressure, and cholesterol. And in this, we are going to also split the data into 80 to 20, thus train and test with feature standardization to ensure fair comparison across models. The outcome is going to be the best model selected based on highest AUC supporting effective diabetes risk prediction and informed clinical decisions. Hence, our output is diabetes model comparison. Logistic, it's at 0.847, random 0.847. That means that here the output is slightly or almost similar according to the comparison. Lastly, we're going to talk and actually have to just emphasize on the diabetes AI pipeline, of which required libraries we have there and data preparation we train, we split as we have been doing. And in this last one, we're going to actually have to just we're going to actually have to use important health measures like body mass index, high blood pressure, high cholesterol that affect diabetes risk. Divide the data into 80% for training and 20% for training to check how well the model works on new patients. And we're going to actually also have to adjust the value of predictors, as we can actually just see through our confusion matrix that actually have to just shows the actual and the predicted. Just as we also have on the other side here another model and another visualization that actually shows the actual and the predicted diabetes risk. And also, we also have the diagnostic performance, of which actually have the matrix of accuracy, precision, recall, and F1 score, and these are the outputs that came with it. And this have to just make our final presentation of our application and our prototype and our model. Thank you very much.